You ever notice how some shapes just show up everywhere, in all these different places? Well, it's not a coincidence. It's almost like there's this hidden mathematical language writing the story of everything, from a simple basketball game to, space travel. So, let's get into it.
Okay, take a look at this. We've all seen this a million times, right? That graceful, predictable, just perfect arc of a basketball as it sails toward the hoop. It's just a beautiful curve. And actually, fun fact, it was Galileo who first figured out that this is the path any object takes when it's just flying under the pull of gravity. But that arc, it gets you thinking. So, here's a question for you. What on earth could that basketball shot have in common with, well, this, a satellite dish? I mean, think about it. One is just pure physics in motion, a ball flying through the air. The other is this piece of high-tech engineering, built to grab these super faint signals out of deep space. They seem totally unrelated, right? Well, believe it or not, the answer is this really deep, kind of elegant connection. Both of these things, the basketball shot and the satellite dish and a whole bunch of other stuff, are shaped by one single family of curves. They're called conic sections, and they're all related, all born from the exact same simple idea.
Okay, so, conic sections. Where do they come from? You might be surprised by how simple the answer is. It all starts with one shape, a cone. Yeah, just a basic cone. Let's see what happens when we start slicing it up. So imagine you have a flat plane, like a knife, and you slice right through that cone. Now, if you get the angle just right, perfectly parallel to the slanted side of the cone, the new edge you create, that curve, that's a parabola. And look at that. It's the exact same arc as our basketball shot. But what if we change the angle just a little bit? Let's say we tilt that slice, so it's not quite so steep. Suddenly, the curve closes up on itself. It's not an open arc anymore. This beautiful complete loop, that's an ellipse. And for our last trick, let's make the slice really, really steep. So steep, in fact, that it cuts through both the top and bottom parts of a double cone. When you do that, you get these two separate mirrored curves. That's a hyperbola. So think about that for a second. The parabola, the ellipse, the hyperbola, they're not really three different shapes. They're just what you see when you look at a cone from different angles. Kind of cool, right? All right, so we've got these three amazing shapes, all from one cone. But to really get a grip on their power, let's zoom in on the one we probably recognize the most, the parabola. Let's figure out what really makes it tick. So let's forget the cone for just a minute. There's another, maybe even cooler way to define a parabola. Just think of it as a shape you draw by following one very specific rule. All you need are two things, a single dot, which we'll call the focus, and a straight line, which we'll call the directrix. The parabola is the collection of every single point that is the exact same distance from that focus point and that directrix line. And this diagram makes it super clear. See, pick any spot you want on that red curve. Now, measure the distance from that spot straight to the focus point. Then, measure the distance from that same spot straight down to the directrix line. Those two distances will always be exactly the same. It's that perfect balance that creates the classic parabola shape we all know. And this is the why behind our basketball shot. The ball is moving forward, but gravity is constantly pulling it down. That constant tug of war forces the ball to follow a path where every single point on its journey perfectly obeys that focus directrix rule. So it's not just a nice-looking arc, it's a mathematically perfect parabola. Okay, but here's where it gets really cool. This very specific geometric property, it gives the parabola a kind of superpower. Seriously, and it's a power we use every single day in some of our most important pieces of technology. So here's the secret. Take any ray. Could be a ray of light, a sound wave, a radio signal, whatever. As long as it comes in parallel to the parabola's main axis, it will hit that curve and bounce directly to that one special point, the focus. It's like a magnet for parallel rays. Every single ray, every single time.
Now you can probably see why this is so incredibly useful. This ability to gather up all this scattered energy and concentrate it in one spot, it lets us take faint, weak signals and make them powerful enough to use.
And that brings us right back to our satellite dish. That parabolic shape is not just for looks, not at all. It's designed to catch all those incredibly faint TV signals coming down from space, and then reflect them all inward, focusing them with perfect precision right onto the little receiver. And guess where that receiver is? Yep, right at the focus.
But wait, there's more. This superpower, it works in reverse, too.
If you can use a parabola to gather energy in, you can also use it to shoot energy out in a focused beam.
It's the exact same idea, just flipped. This time, you put a light source, like a light bulb, at the focus of a parabolic mirror. What happens? All the light rays hit the mirror and then bounce outward in a perfectly straight parallel beam. This is exactly how your car's headlights work, or a good flashlight. It's how they create that powerful, focused beam instead of just scattering light everywhere.
So, the parabola is pretty amazing, right? But let's not forget about its cousins. The ellipse and the hyperbola are just as important, and it turns out they shape the very paths of planets and comets out in our solar system.
Yeah, it turns out planets don't actually orbit the sun in perfect circles. It's something the astronomer Kepler figured out centuries ago. Their paths are actually ellipses. And the sun isn't right in the middle either. It's located at one of the two focal points of that ellipse.
This chart here gives you an idea of just how squashed or elliptical those orbits are. The number we use is called eccentricity. 0 would be a perfect circle. Now look at Earth, we're at 0.017. That's super close to being a circle, which is pretty stable. But then look at poor Mercury, way up at over 0.2. That means its distance from the sun changes a lot, which is why it has these massive temperature swings throughout its year.
So what about the hyperbola? What does it do? Well, it describes the path of things moving so fast that they can actually escape the sun's gravity. So if a comet is on a hyperbolic path, it's basically just a one-time tourist. It swings by the sun once and then gets flung back out into deep space, never to return.
So just think about it. From one simple action, slicing a cone, we get the exact curves that describe a basketball shot, a satellite dish, a planet's orbit, and a comet's final goodbye. These elegant shapes are like a fundamental part of the universe's code. It really makes you wonder, right? What other hidden math is out there shaping the world we see every single day?